Sometimes it is desirable to implement a system based on subsystems of first or second orders. The subsystem have a small order, first order or second order. These has such an implementation might be desirable when we have modules of a first order and second order systems. And when we want to implement a more complex systems, we can simply put together these modules to make it a more complex system. And these first order and second order systems are also more easier to understand and to design. We will talk about one more advantage of implementing a system based on subsystems of smaller orders later when we talked about coefficient quantization. Suppose we have a nth order system like this. We have Hz. It has a1z inverse all the way to anz minus n, and the coefficient b0, b1 all the way to bn. And like before, we have set the first coefficient, this is supposed to be a0 to be 1 without loss of generality. One possible way to do this is to use Cascade Form. To use such a form, we factorize h for the numerator. Suppose the zeros of h are zk. K goes from 1 to n. And the poles are pk. K goes from 1 to n. We factorize the denominator and the numerator. And we pull out the coefficient b0. And now we have hz in factorized form. Now we have n first order system, and we can implement these n first order IIL system in Cascade Form. Very often, the system that we are concerned with have real coefficient. The coefficient hn are real. In this case, the poles of h are complex conjugate pairs, except those on the real axis. Similarly, the zeros are also in complex conjugate pairs, except those on the real axis. Then we can combine those pairs of complex conjugate poles or zeros to make it a second order. Let's say after we combine the coefficient are ck, z inverse, plus dk, z minus 2, and then 1 plus ek, z inverse, plus fk, z minus 2. And some of those may not encompass conjugate pair because they are zero or poles on the unit circle, and we can simply make these coefficient dk equal to 0, fk equal to 0, then it will become a first order system. So actually these could be a first order, and we have put L here instead of n over 2 because some of them may be real pole or real zeros. And let's call each of these terms to be hk of z. This is hk of z. Then h can be written as a product of these hk. K goes from 1 to L. When we implement the system, h, we can implement it as a cascade of these subsystems. These are all systems of a smaller order, so we call them subsystems. H1, Z, H2, Z, 2X, HLZ. For Cascade Form, we express HZ as a product of smaller order terms. Now, let's consider a very similar case, parallel form, that express H as a sum of smaller orders. For parallel form, we express H as a sum of first order term. There are n such terms. and a constant. Similarly, when h has a real coefficient, we can combine those terms that are complex conjugate. The terms that have complex conjugate poles together have a real coefficient, second order sections. After we combine those complex conjugate poles, then the coefficient of the second order system would have a real coefficient, ek plus fkc inverse. We would get real coefficient systems. Similarly, this is a general expression. This can be a first order, maybe first order. And we can call each of these subsystems hk. Well, this hk is different from the hk in cascade form. And we can implement the system in terms of these subsystems. We would have a bunch of subsystems, a bunch of all these subsystems, and when the input comes in, one that will be multiplied with a beta 0, and the other will go through h1 to hl minus 1, and the output are all added up, and this is the output. And here we have a bunch of adding note here. And there's the parallel form implementation. Earlier our discussion had mostly on the implementation, how to implement a system when we are given a system function. Now we're going to ask the question, a related question, but slightly in the converse. That is, suppose we are given a signal flow graph. We already have an implementation. How do we know what the system function is? Suppose we have input here, we have output here. Here, right in the middle, we have a branching node, and this one goes this way, this one goes this way, and this one has a multiplier alpha 1, and this is a branching node. This is a branching node, and right here we have another branching node. It will come this way to here, and here we would have more than one. There's a scalar alpha 2 on this branch, and right here it will come this way, and this goes this way, so this will make this a adding node. And on this branch we have a z inverse, on this branch we have a z inverse, and the output of this z inverse, here's another branch, it will come this way, shoo, to here. So right here at this node has one input, and one input coming down this way. This is minus alpha 2, and also one input coming. So this one input, it has 3 inputs actually and one output. So it's a adding node as well. Right here, there's a crossing here, but it doesn't have any node. It's just a branching because of a drawing. The lines are crossing, but there's no node here. How do we find the system function for such a system? Parenthesis here. How can we find this system function? As a good rule, we can usually give some names to store it in the delay. So for example, let's say this one, the output of this node here is Wn. Then the output of the delay element will be Wn minus 1. And the output of another delay element will be Wn minus 2. Okay, so that's the output of that. Because here, if this is Wn, and at the output of the delay, it will be Wn minus 1. And then another delay, so it's Wn minus 2. Now let's try to find out how W is related to X and Y. W here, W is this one here, right? So this is the same as the output here. W actually depends on one is xn. This one is xn, and also depends on this one. Adding node has added, the adding node adds 3 inputs, 1 input, 2 input, and 3 input. Okay, this input is xn. This input comes from this view, come from here. So it's minus alpha 1 w and minus 1. That's the top one here. And then the second one comes from here. It's wn minus 2 multiplied with a minus alpha 2. So it's minus alpha 2 wn minus 2. And then the third one is xn. So that's what wn is. And now let's look at yn. What is yn? Yn is the output of this adding node. And it adds up from wn minus 2. And from here, wn minus 1 alpha 1 comes here. And then a third one comes, this is wn alpha 2. So let's write them down. There's a alpha 2 wn. And then there is alpha 1 wn minus 1. And then there is wn minus 2. Now we have two difference equations. We can apply the transform and the difference equation and difference equations and see what if we can get the system function from here. If we apply the transform and the first difference equation, we get wz. And then we also have term that is alpha 1 wz, but with the z inverse. And we also get w2 and wz with the 2 z inverse with the 2 delays. And then we get xz. We can move these w to the left hand side and we get plus here, and this is equal to xz. Now we can pull out wz here, and we get 1 plus alpha 1z inverse plus alpha 2z minus 2 and xz. So that's how w and x are related. Now let's look at the second difference equation. For the second difference equation, we apply the transform, and then we get yz equal to alpha 2 wz and a alpha 1 wz z inverse, and then z minus 2, and every one of them has a wz, so we can pull them out. Now combining these two equations together, wz is given in the first equation, right? What we need is the system function, which will relate x and y only, so we want to remove w somehow. W can be written as xz divided by this term. So let's continue on writing this equation here. Then we get alpha 2 plus alpha 1 z inverse plus z minus 2, and then 1 plus alpha 1z plus alpha 2z minus 2 xz. So what is the system function here? The system function? We are looking at the system function here already, right? This is our system function h. That will be the system function from x to y. Now let me ask you a question. What kind of system is h? What kind of filter? We have actually talked about this type of system in chapter 5. It has a very special property. The property is that it has coefficient 1 and then alpha 1 and then alpha 2. For the top, the coefficient is alpha 2, alpha 1, and then 1. It's the flipped version of the coefficient down here. So what kind of filter is this? It is a O-pass, isn't it? And this is just a second order IIR filter. We can, of course, implement it using the direct form 1 or direct form 2 structure that we have talked about earlier. We can implement it using this direct form 2, which is minimum. But why do we want to implement it using such a structure? Let's look at the picture again, the signal flow graph again, and let's see the number of multiplier, adder, and delay in this system. What is the number of delay for such a systems? And the multiplier and the adders. For delay, we have only 2 delays, right? Okay, so the number of delay is also 2. It will make it a canonical system. And how about the number of multiplier? Number of multiplier is, we have a 1, we have 2, and we have 3. We have 3 multiplier. How about adders? Adder, let's see. This is a branching node, and here we have an adding node, and this is a branching node, a branching node, adding node. So there are only 2 adding nodes, 1 here and 1 here. And this adding node, it adds up 1, 2, 3. 3 signals together. So it's actually, although there's only 1 adding node here, it would take how many adders? It would need 2 adders here. And how about this one? It has 1 input, 2 input, and a 3 input. So again, 3 inputs, so 2 adders. So altogether we have 4 adders. Now let's compare this with the, for example, direct form 2 structure that we have talked about. Is there any difference in the number? Usually with a direct form 2 structure, for such a system, we will need how many multiplier? We will need 1, 2, 3, 4. So if we implement the O-pass system like this, we only need 3 multiplier instead of 4. Earlier when we talked about structures for rational systems, the structure can be used for both FIR and IR. But now let's talk about structures for FIR. For the special case that the system is FIR, let's talk about it some more. When we have HZ that's given in this form, let's talk about the implementation. And what we are going to talk about here, some part will be very similar to what we have talked about earlier. For a mth order FIR system like this has an n plus 1 coefficient, and when we write down the difference equation, the output yn can be written in terms of the inputs like this: xn h0, xn minus 1 h1, all the way to xn minus m hm. And when we draw the signal flow graph, we would have one delay, another delay. Altogether, we need a total of m delay because we have xm. And here's the input x. xn will be multiplied with h0. And xm minus 1 multiplied with hm minus 1. All the way to the last one, that is hm. And all these will be added together. So we have an adding node here. This is a branching node, and right in the middle, this is continue like this, and this is yn. And if we look at the number of multiplier, adder, and the delay, it would be the number of multiplier, and delay would be easy. It's equal to m. And the number of multiplier, we simply count the number of coefficient here. We have h0. Oh, this one is h1. Fortunately, this one is h1. Okay, all the way to hm. And the number of multiplier, we count the multiplier here, 1, 2, all the way to m. So we have m plus 1. And adders, we are adding m plus 1 numbers together, so we need m additions. This is a direct form implementation, and we can also have transpose form. The transpose form of the above structure will simply be like this. hm minus 1 all the way. This one is h0. This is the inverse all the way to the inverse. This is yn. We will leave this as an exercise. We can also have cascade form like before, and when the case that hn is real, we can combine complex conjugate poles together. Then we may have terms like this: b1k the inverse plus b2k the minus 2. And again, each of these second order term can be a first order. So far, this is just like what we had talked about before. Now we want to mention a little bit something that is different. That's the structure for generalized linear phase FIR. For example, we have an Hn that has a generalized linear phase. And suppose this is the impulse response like this. This is the impulse response. Here in this example, we have m equal to 5, 1, 2, 3, 4. And this is the impulse response, Hn. Now let me draw the direct form like before. The direct form implementation will require 1, 2, 3, 4, 5 delay, and we would have multiplier as well, h0, h1, h2, h3, h4, and h5, and the output are added together. This is the input, this is the output. And we have adding node to add them all up. And like our discussion earlier, we would need 6 multiplier, and we need 5 adders. Oh, I forgot this one, h5 here. Okay. And one thing that we may notice is that because this has generalized linear phase, so the coefficients are symmetric. So in fact, some of these coefficients are identical. This coefficient, for example, h0 will be the same as h5, and h1 will be the same as h4, h2 the same as h3. And that would give rise to the question of, is it possible to combine these multipliers, and perhaps we can reduce the number of multipliers? We can see this by writing down the difference equations. h0 xn, h1 xn minus 1, h2 xn minus 2, and then h3 n minus 3, h3, but h3 is the same as h2. And also xm minus 4, h4 is the same as h1. And then xm minus 5, H5, which is the same as H0. So now we can combine like this. First we add xn and xn minus 5 and multiply it with h0. And then we also have xn minus 1 plus xn minus 4. Together they are multiplied, that the sum is multiplied with h1. And then we also have h2. Here we have xn minus 2 plus xn minus 3. And this will suggest another implementation for h. So now when x coming in, we have 5 delays xn, and the delay, 1 delay, 2 delay, 3 delay, 4 delay, 5 delays. And first of all, we'll see that xn and xn minus 5 will be added together. So now we would have xn and x5 that's added together. We have an adding note here, a branching note here. When it's added together, it's multiplied with h0. xn minus 1 and xn minus 4 are added together. xn minus 1 and xn minus 4, they are added together, and the result is multiplied with h1. And then the signal xn minus 2 and the signal xn minus 3 are added together, and the sum is multiplied with h2. And when we add them all up, we get the output yn. Notice that here's a branching note. Here's a branching note. And although there's crossing here, there's no note here. There's no note here either. And now if we look at the structure again, we still need 5 delay. But what is the number of multiplier that we need in this case? The number of multiplier is now 3 instead of 6 in the original case. And the number of adder? The number of adders, we can count the number of adder. It would be 1, 2, 3, 4, 5. The number of adders remains the same as the original case as in the direct form implementation. So in this case, the number of delay adders are the same, but the number of multipliers are actually halved. And it can be verified that for the nth order case, the number of multiplier around half the direct form implementation. You can verify this for all 4 types of generalized linear phase filters.